Have you ever imagined how maglev trains work? Some people say it is like magic. In this presentation, we will explain everything you need to know about maglev trains, including the history of development, how it's working, and what are the improvements we can do in the future. The word maglev comes from the word combination of magnetic mag and levitation lev. What exactly is the maglev train? Maglev train is a floating vehicle for land transportation that is supported by either electromagnetic attraction or repulsion. These trains eliminate the need to use the conventional train wheels and tracks because it uses powerful magnet to levitate and propel the train forward. How does it work? The basic idea of maglev train is the same as when we play with magnet, as everyone already knows that if we take two magnets with the same poles, it will repel to each other. Meanwhile, it will attract if we take two magnets with different poles. Now we already know what is the maglev train basically is, but when exactly maglev train was built and what was the history of its development? The history of maglev trains began in 1934, when the first concept was proposed by Hermann Kempe in Germany. In 1966, the train achieved its first successful test in United Kingdom, reaching a speed of 167 km per hour on a test track using electromagnet propulsion. In 1984, the first commercial maglev train, the Linimo, began its operation in Aichi, Japan. The Linimo successfully achieved a speed of 100 km per hour on an 8.9 km track. In 2003, Shanghai maglev train opened in China. It became the world's first commercial high-speed maglev train, connecting Shanghai Pudong International Airport to the city center and reaching a top speed of 431 km per hour in just 7 minutes. In 2015, the Japanese maglev train broke the rail vehicle speed record by reaching 590 km per hour. So, what is the significance of maglev trains? Maglev trains are significant because they enable faster intercity connectivity and reduce travel time. They also support sustainable transportation by lowering energy consumption. Furthermore, maglev systems reduce long-term operating costs, making rail transportation more reliable and economical.
But first, how does a maglev train levitate? There are multiple ways to levitate a train using magnets. The first method is used by the Shanghai maglev train called electromagnetic suspension, or EMS. For EMS, the train can either be levitated using repulsive force of the magnets or be levitated by attraction force of the magnets. As we know, magnets with the same poles will repulse each other. This action will cause the levitation effects by preventing the top and bottom magnets from contacts. But this method requires high precision to maintain constant distance between the two magnets. However, the second method uses EDS to levitate the train, which goes for electrodynamic suspensions. This method was used by the Chuo Shinkansen in Japan. As for EDS, the maglev train needs to be moving at high speed before the effects of levitations can occur. This is because the EDS utilizes Faraday's law, which states a changing magnetic environment around a conductor induces an electromotive force which drives an electric current. However, this method needs the magnetic force to be as strong as it can to ensure stability of the train during high speeds. Then, the principle of Lenz's law was used to stabilize the train. Lenz's law states that an induced electric current in a conductor flows in a direction that opposes the change in magnetic flux that created it, essentially resisting the change in magnetic field. According to Ohm's law, I equals to V over R, we can significantly reduce the resistance by making the conductor a superconductor by cooling it with liquid nitrogen. By reducing the resistance in the coil, the current also increases. However, this current is actually a special type of current called eddy current. It produces a repulsive force to help the train levitate and help dampen uneven terrain. The key difference between the Shanghai maglev train and the Chuo Shinkansen is the method used to levitate. The Shanghai maglev train used electromagnetic suspensions, and the Chuo Shinkansen used electrodynamic suspensions and superconductor to function properly. Now, how does a maglev train move forward? We first have to look at electric motors. A maglev train uses an electric linear motor to propel itself forward. The basics are electromagnets are placed on both the train and on the rails. However, the electromagnet on the rails are supplied with alternating current or AC. When a conductor is supplied with current, it produces a magnetic field. This is how electromagnets are made. The electromagnets function like normal permanent magnets. The same poles repulse each other, which creates a pushing force. On the other hand, when there is a difference in poles, the two electromagnets attract each other, which creates an attractive force. This allows the train to be propelled forward in the same direction as the repulsive force. But why use alternating current? Unlike a normal electric motor, which uses a direct current and a commutator to achieve a constant motion, an electric linear motor uses an AC to alternate the polarity of the electromagnet to produce a constant forward movement.
Let's look at the real-world implementation of maglev trains. One major example is the Shanghai maglev train in China, which connects Shanghai Pudong International Airport to the city. The train covers a distance of about 30 kilometers in under 8 minutes, with a maximum speed reaching 430 km per hour. This system demonstrates how maglev technology can be successfully applied for high-speed public transportation. Another example is the Incheon Airport maglev in South Korea, which serves a shorter urban route around Incheon International Airport. Although it operates at lower speeds, it shows that maglev technology is suitable for urban and airport transport, offering smoother and quieter travel compared to conventional trains. In addition, Japan's SC maglev project is currently under construction. This superconducting maglev system has achieved test speed of over 500 km per hour and is planned to significantly reduce travel time between major cities such as Tokyo and Nagoya. These examples show that maglev trains are not just theoretical concepts, but practical transportation systems already implemented and expanding in the real world.
Now, let's talk about the potential benefits of maglev trains. Maglev trains can reach speeds of up to 630 km per hour, making them ideal for long distance travel. This helps to reduce travel times by allowing passengers to reach their destinations more quickly and conveniently. Unlike traditional trains that rely on wheels and friction, maglev trains float above the tracks by using powerful magnets, which eliminates friction and enable much higher speeds. Another benefit is energy efficiency. Maglev trains require less energy than traditional trains. This is because the absence of the wheel reduces the friction, which lowers the energy needed to propel the train forward. Finally, maglev trains face less maintenance issues. This is because there is no direct contact with the tracks, which leads to less wear and tear between components. The electromagnetic levitations eliminates the friction damage, which means fewer repairs are needed. This saves operators both time and money, while passengers benefit from more reliable service. However, there are some challenges that need to be considered when it comes to maglev trains. The first thing is high cost of construction. Building a maglev system requires a huge investment in infrastructures. Special tracks, guideways, and power systems must be constructed, which makes overall construction costs more higher than conventional rail. Another challenge is limited infrastructure. Maglev tracks are not compatible with traditional rail networks. This means new infrastructures must be built entirely from scratch, adding both cost and complexity to projects. The last challenge is high energy consumptions at higher speeds. Maglev trains are efficient at moderate speeds, but once they go faster, the energy demand rises quickly. High-speed travel creates a strong air resistance, and this makes the train consume more electricity than conventional rail.
I will explain the future developments of maglev technology. In the future, maglev trains are expected to reach higher speeds of up to 600 km per hour, which can reduce travel time between cities. Another important development is the use of vacuum or low-pressure tubes. These tubes reduce air resistance and allow the train to travel much faster. Lastly, more countries are planning to adopt maglev systems as part of their future public transportation networks. Next, I will explain the main innovations in maglev technology. One key innovation is the use of superconducting magnets, which produce strong magnetic forces with very little energy loss, allowing stable levitation. Another innovation is smart control systems that use sensors and computers to improve safety and efficiency. Finally, technologies such as Magrail allow maglev systems to be built on existing railway tracks, which helps reduce construction costs and time.
In conclusion, maglev trains represent a major advancement in modern transportation technology. Using magnetic levitation, these trains operate without physical contact, allowing for smoother and faster travel. Maglev technology have been implemented in real-world systems such as the Shanghai Maglev in China and the Incheon Maglev in South Korea, with Japan's SC Maglev currently under development. While maglev trains offer faster intercity connectivity and improved efficiency, they also face challenges including high construction costs, high energy consumption at higher speeds, and limited infrastructure. Nevertheless, maglev trains have strong potential to play an important role in the future of high-speed transportation.